Today we're going to be looking at Horoscope, which is an easy pwn challenge from San Diego CTF 2022. The challenge may be easy, but due to the nature of the pwn category, even with the most basic beginner challenges, there can often be a lot of assumed knowledge and required expertise to get started. I will do my best to strike a balance between taking the time to explain the fundamental concepts and assuming you know a lot about binary exploitation. The prompt briefly reads, "This program will predict your future," and then it provides a connection command. We, the challenger, are provided with the compiled binary and nothing else. The first and most important thing that I would recommend doing is just running the binary and getting a sense for the program itself. Nothing bad could happen, right? The binary will ask us to input our birthday. I will now enter the birthday of the viewer watching this video. Well, odds are one of you is freaked out. Lucky you, according to this program, everything is going to be just fine. Let's try running that again, but this time I'm going to cram as many characters as I have the patience for into the input. Given that this is the only input we have to work with, and given that there is likely a memory corruption vulnerability in this program, this would surely cause a seg fault if we enter enough characters to overflow the buffer. Unfortunately, if we enter nonsense, we don't get the seg fault we want, and instead the program complains that we didn't enter a valid date. This usually means that there's some kind of check that the format requested here is indeed reflected in the user's input. So we'll have to append our A's to the end of a correctly formatted date. Upon doing this, we get the seg fault we wanted. Okay, I think we've done enough recon on this. To really start analyzing this binary, I'm going to open the binary in Cutter, which is a disassembler similar to IDA or Ghidra. Cutter is not only free and open source, but it is just a little bit easier to use than those other two options, so I thought it would make a good choice for this video. Once Cutter loads it, we get a bunch of very helpful information right away. For example, it lets us know that the NX bit is indeed set, so we will need to overwrite the return address to do anything interesting. It also tells us that this binary was not compiled with stack canaries enabled, which means that overwriting the return address should be rather straightforward and not require any wizardry. Glancing at the functions column on the left, the only functions that are not normal libc built-ins are main, debug, process input, and test. Starting with main, we can look at the disassembly for this function, but since this isn't necessarily a reversing challenge, I'll go ahead and cheat by switching over to the decompiler view. From here, just by how little code there is here, the vulnerable code in question is probably this call to fgets right here. We're filling some buffer from standard input up to size 140 hex, but this buffer that we're filling must be a lot smaller than that to be causing a seg fault. We can also see that this buffer gets passed to the process input function. Looking at this, we can also see what might be those formatting checks, as well as a switch case table. The switch case really only has two cases: the default, where you enter a non-valid date, and everything else, which simply causes the month that you entered to be printed, and then you will be told to look forward to your great week. This is a shame because I really felt special when it told me my horoscope earlier, but now I don't feel special at all. Anyways, I think the only thing we have to worry about in this function is passing this check so we don't exit early. That way we can get to the end of this function and return to main, where we will then hopefully return to an address of our choice. Let's look at the other two interesting functions here. This test function performs a check against the global variable temp, and if it has been set to 1, it will quite literally pop a shell for us by calling system with the path bin.sh. This test function is clearly our quote-unquote win function that we have to return to, but there is a slight hiccup in the sense that this temp variable needs to be set to 1 before that happens, and we can't set that variable ourselves. This, however, brings us to the debug function, which does exactly what we need. At this point, it becomes obvious that what we are intended to do is to write two return addresses to the stack. The first one should call the debug function, which sets the temp variable equal to 1, and then the next return address, which is called immediately, should be the test function, which actually pops the shell. Binary exploitation can be difficult enough, but I find it's even harder to follow when someone else is writing the exploit. So to show you what's going on, I've created a little visualization of the stack which will show how our exploit will take control of it. Take a look at this spreadsheet. Yes, I know, trust me. The top of this represents the higher addresses of the stack, and the bottom of this represents the lower addresses of the stack. You'll want to remember that the stack grows downward towards the lower addresses like so. We are currently inside of the main function right before the buffer overflow has occurred. This is where the original stack buffer variable s is stored on the stack, and this is the space allocated for it. We're going to overflow that and corrupt the previous base pointer, as well as write some return addresses here. Once the buffer overflow occurs, we've written our initial valid payload, a bunch of A's until we get to the offset we need to be, and then we write our two function pointers, the first one to debug, and then the second one to test. Even after doing this, nothing happens right away. The program continues and calls into the process input function like normal. This corrupted stack frame is left alone while process input does its thing. When the process input function returns, the main function is ready to return as well. Remember that there are two parts to a return in Intel x86, the leave and the actual return. When the leave is called, the stack pointer gets set to the base pointer, and then the base pointer is popped off of the stack, which decrements the stack pointer again, so the stack pointer is now pointing towards our first return address. The base pointer has been loaded with the value of all A's, which is just garbage. This will eventually cause a seg fault, but not before executing our ROP chain. When the return executes, you'll notice that we are now executing at the address that was pointed to at the top of the stack, and we have now taken control of the instruction pointer and pointed it towards the debug function. The debug function will execute, and when it finally returns, that will pop the next return address off the stack and put us in the test function, which will pop the shell we want. Okay, now that we know what we want to happen, how are we actually going to go about doing this? Well, the best way would be to use pwntools, which is a Python library specifically designed for binary exploitation. You could probably use it for every challenge in this category. To start using pwntools, we import it, which immediately vomits a bunch of nifty functions into our global scope. The process function will allow us to attach to the binary and send and receive input from it. In our case, we will want to send input after the program is done prompting us, and it has a handy function for this called sendLineAfter. We simply tell pwntools the phrase to wait for, which I think in this case would be your very own horoscope. Don't forget to also include the new line character. Then we can just tell it to send after it sees that line, which in this case will just be our dummy valid input. Then, by convention, it's usually standard to interact with the process after the payload has been sent by doing proc.interactive. You can run this and it will do the input exchange, but it doesn't do anything else interesting. Because we're not exploiting it yet, the program simply exits immediately. Going back to our solve script, there are three parts to this payload. We're going to need the valid input, and we already know what that's going to look like. We'll need padding, which will just be a series of A's, but the number of A's has yet to be decided. Lastly, the return addresses of the functions we want to execute. Let's start with the padding. The easiest way to figure out the amount of padding we need is to go into Cutter. It has analyzed this character buffer variable we want to overflow called s, and it's figured out that it's about 38 hex away from the base of the stack. Therefore, we will need to write 38 hex characters before we get to the return address we're interested in. So we'll set the padding to the character A times 38 hex, but we have to remember that the valid input will use some of our characters, so we'll subtract away the length of our valid input to make sure we fill the gap just right. Next up, we need to find the return addresses of the debug function and the test function. We could easily view these in Cutter, but I want to show that what a lot of people would do in this situation is to use the ELF parser built into pwntools. To use this, we simply call ELF on the binary, and now we can access various symbols inside of it. For example, elf.symbols debug is going to be the address of our debug function. Unfortunately, this address is currently a Python number, and we will need to format it as a little endian byte string in order for the Intel x86 processor to understand it. Thankfully, PwnTools provides the functionality to do that as well. You just pass it to the p64 function, and it will return the correctly formatted byte string. After our debug return address, we can append that to our test symbol that we will use as our next return address, and that should make up our ROP chain. Now we can add all three of these components together to create our payload, and we can pass this payload into the process. This should be enough to execute the exploit. We could try it out by running the Python script, and when we are dropped into interactive mode, we can actually type commands because we have successfully popped a shell. If I type ls, I can see a flag.txt file in my current directory, and if I cat this text file, I have captured the flag for this pwn challenge. One last thing. There's actually an even easier way to solve this challenge while only writing one return address. It's important to keep in mind that we don't have to jump to the top of functions, and very often we don't want to. Rather than calling the debug function and then the test function, we could have just more easily jumped to the line inside of the test function where system is called. By opening up Cutter, we can find the precise address inside of the if statement where system is called, and we can use this address as the address to return to in our exploit. If we modify our script and try it out, we can see that it pops a shell just like our first method. Either approach should work, and the first approach is probably the intended solution, but with more advanced challenges, you will often need to get more creative about where you're jumping to, just like this.